Now let us begin the topic of three-dimensional geometry by learning about some of the terminologies that we will be using here. The first one is what is called as direction angles of a line in 3D space. So by direction angles, what we mean is, let us consider the basic frame of reference, that is x, y and z axis and the origin. Let's consider that there is some line. Okay. Now if we measure the angle that the line makes with positive x-axis, we call that angle as alpha. Then the angle made by the line with positive y-axis, we call it as beta, and the angle made by the line with z-axis we call as gamma. So these three angles are called as the direction angles of the line. Basically these angles tell us how inclined that line is with respect to the three coordinate axes, right? Now in addition to these angles, we further define what is called as direction cosines of a line. Now direction cosines are nothing but merely the cosines of direction angles of that line. So we saw that the direction angles were alpha, beta and gamma. Hence if we take the cos of those direction angles, we get what is called as direction cosine. Okay. And these direction cosines are denoted by symbol L, M and N respectively. Right. So therefore L, M, N are the symbols for direction cosines of a line. Now we will derive one very important relationship between L, M and N, that is direction cosines of any line. Okay, so that relationship is given by L square plus M square plus N square is equal to 1. So for any line, sum of squares of its direction cosines is always equal to 1. Okay, so now let's prove this. For that, let us consider any general vector. Okay, let's consider the general vector OP bar. Okay, so where P is this particular tip. Alright, let's call R as the magnitude of that particular vector. Now from this point P we are dropping the perpendiculars on all the three axes, so therefore we get a box like structure, the rectangular parallelepiped or cuboid. Alright, now let us show the angles. That is, we know that the alpha is angle between the line and the x-axis, and similarly we have beta and gamma, the remaining angles. Now let us draw the diagonal of the rectangular base. Okay, so let us call as that Q. Then let us give the names to the points. So now let us consider that we have joined A and P. Okay, now if you look at this particular triangle, that is triangle OAP. Okay, let me highlight it. Triangle OA and P. This triangle is actually a right angle triangle, because if we look from the direction as shown here, the triangle will look like this one. So here is O, here is P and here is A, and this angle is alpha and this is R. So clearly OA, correct, which is the adjacent side of angle alpha, so OA, its magnitude, so we don't show the vector, has to be nothing but R cos alpha, isn't it? So that means we are talking about this distance, that is R cos alpha. Similarly OB, that is this distance, that will be R cos beta, and OC, this distance will be R cos gamma. Okay, so we don't show that because that is clearly following from this particular explanation. So now what do we do is, if you observe in triangle OPQ, right, angle PQO is a right angle. So therefore OP square is equal to OQ square plus PQ square. But OQ square can be written as OA square plus AQ square, because if you look at the triangle OAQ, that itself is a right angle triangle whose hypotenuse is OQ. So therefore OQ square can be broken as OA square plus AQ square plus PQ square. Right? Now OA is nothing but R cos alpha, then AQ is same as OB, right? So therefore that becomes R cos beta the whole square, and lastly PQ is nothing but OC, which is nothing but R cos gamma the whole square, and OP itself is R, so OP square is R square. So therefore on squaring we get that R square can be cancelled from all sides, so therefore we get 1 is equal to cos square alpha plus cos square beta plus cos square gamma. But we know that cos alpha, cos beta and cos gamma are nothing but direction cosines, that is LMN. So therefore writing in symbols we get L square plus M square plus N square is equal to 1 as required. So this is a very important relationship among L and N. Okay, let's move ahead and see important points or some shortcuts that we use in solving the sums. So note, if a unit vector is resolved into its I, j and k components, then the coefficients of I, j and k are the direction cosines of that unit vector. And this clearly follows from the fact that if we take the magnitude of a unit vector, that has to be equal to 1. So therefore in order to have that as 1, the coefficients of I, j and k must be nothing but L, M and N, because we know the relationship between L, M and N is L square plus M square plus N square is equal to 1, right? And direction cosines of x axis are 1, 0, 0, y axis are 0, 1, 0, and those of z axis are 0, 0, 1. So here also it can clearly follow if we draw the figure. Let's consider x, y and z axis. Now suppose we want to consider the direction cosines of x axis. So let me show the x axis in green. Now the angle which x axis makes with itself is nothing but 0 degrees, isn't it? Then the angle which x axis makes with y axis is nothing but 90 degrees, and the angle which x axis makes with the z axis, that is also 90 degrees, and hence the direction cosines of x axis are nothing but the cosines of these direction angles. And since cos 0 is 1 and cos 90 is 0, therefore we get the direction cosines as 1, 0 and 0. Similarly we can easily show the direction cosines for y and z axis also.